All right, this is our just-in-time lecture for 11.5, Molecular Orbital Theory, the Basics and Diagrams. The first question that gave us trouble asked, each oxygen atom in O2 has blank electron groups around it. If we look at O2, we see that we've got 1, 2, 3 electron groups. And that's important because we're going to need to hybridize orbitals to fit all those groups around oxygen. All right, so to get those 3 electron groups around each one of these oxygens, we're going to have to hybridize 3 atomic orbitals to make 3 hybridized molecular orbitals. So that would give us 1 s and 2 p's for our 3 hybrid orbitals. Okay, according to Lewis structure and valence bond theory, O2 should have all electrons paired and be diamagnetic. The fact that it is attracted to a strong magnet tells us it's actually paramagnetic, which means that we've got a bunch of oxygens with unpaired electrons. So that's why we had to go to MO theory to explain that. All right, so in MO theory, when we start combining these atomic orbitals, these are the atomic orbitals over here, we get these molecular orbitals, MOs. And we see that the additive part of this gives us a bonding orbital, and we note this with the sigma 1s. So the first piece, we need a sigma 1s molecular orbital, so the sigma star business is out. That means it's an anti-bonding MO. So that's anti-bonding. Anytime we say sigma or pi with a star. And the key is that this additive or constructive interference gives us an MO that is actually lower in energy than the atomic orbitals. There has to be some sort of an energy payoff, or this isn't going to happen. On the flip side of that, if we're looking at the subtractive or destructive interference, this is actually going to be higher in energy. So we're looking now for sigma star interactions because this is going to be an anti-bonding molecular orbital, and it's going to be higher in energy than the atomic orbitals. If you've got this one dropping lower in energy, you've got to see this one going higher to offset that. All right, so this question is actually a twofer. If we want to figure out if something can exist, we first have to look at the molecular orbital diagram and consider how many are in bonding MOs, how many are in anti-bonding MOs, and based on the bond order, you decide, does this exist or not? Okay, so to do that, we're going to start with this question first. And it wants us to find out how many electrons are in the bonding molecular orbitals. So we just saw from this that we have 2 electrons in the bonding MOs. We've got 1 electron in the anti-bonding MO. So if we're calculating the bond order, that's going to be 1/2 times 2 minus 1 gives us a 1/2. So a bond order of 1/2 is not great, but it's enough of a bond to say that H2 minus does exist. So the answer here is yes, it does exist.